Have people been listening to the webcasts? They getting any better? I listened the other day. I could actually hear my voice for the first time. Okay. So, as promised, we're coming up on the first exam. And let's just go over the ground rules again. So, on the syllabus, it said that we were going to have it the week of September 28th. And I think the most reasonable thing to do is have it on that Friday. And typically, I've given exams which I thought would take an hour, but as Brian Frisbee will tell you, every student complains they're too long. So we'll try an experiment this year. I'll design it to be an hour, but you can have 2 hours to do it. And we'll see if it makes any difference in the scores. So you'll have the full 2 hours Friday, October 2nd in class. The exam will cover everything we've done up to that point, including the homework that's going to be due that day. Okay. It's closed book. But as I said, you can bring a piece of paper with anything you want written on it front and back. And calculators are okay, but not computers. And to make my life and the GSI's life a little easier, you have to write in a book like this. We call it a blue book. You can go to the bookstore and buy them. I think they cost $0.25. If you don't have one and forget, which half of you will that day, I'll bring a bunch. Okay. Any questions about that? And as I said before, it's going to be like the homework. So if you do the homework, you'll do fine on the exam, and if not, you won't. Okay. And just as a reminder, we do have office hours, and I would encourage you to take advantage of them if you're having troubles with this stuff. And as you probably noticed, the material is getting more and more complicated. And that's going to be true the rest of the semester. And unfortunately or fortunately, the stuff we did at the beginning, you will need to know to get through the rest of the stuff. So if you had issues with some of the material we've covered before, in particular the quantum mechanics, the angular momentum addition business, please come see us. So I have office hours, and both of the GSIs have office hours. So make use of them. Okay. So at the end of last week, we were beginning to discuss the shell model and the motivation for it. And essentially what we're trying to do is to build up a picture of how you assemble nucleons together to make complex nuclei. And there's a figure in Lily's book, I think it's figure 2.2, which is a little bit misleading. And so rather than show you that, I've redrawn it here in the way I would prefer you to think about it. And it has to do with the fact that we're making nuclei out of neutrons and protons. And all protons are identical to all other protons, and all neutrons are identical to all other neutrons, and they each have a half-unit angular momentum intrinsic spin. And therefore, they are fermions and subject to the Pauli exclusion principle, which says we can only put one particle into one unique quantum mechanical state. And since they have intrinsic spins of a half, each state can actually accommodate two particles because I put one in with spin up and one with spin down. Okay? And so there's a drawing like this in Lily, but the slightly misleading thing is that, remember, when you're putting these protons inside a nucleus, they're all repelling each other, whereas the neutrons are not subject to that electromagnetic interaction. And so when you start filling up the quantum mechanical states, we always start at the lowest energy and put particles in and increase the energy. The initial state for the protons is at a higher energy than that for the neutrons because of this Coulomb repulsion between them. So get used to seeing pictures like this, where this is meant to be a potential well, and it doesn't necessarily have to be an infinite square well, but just for the sake of making the drawing simple, we usually draw them rectangular. And the point is that the base for the protons is higher than the base for the neutrons because of that Coulomb energy. And remember, I showed you that the other day when we were talking about the nucleon-nucleon potential being different for protons than it is for neutrons because of that. So this is the lowest energy state for the protons. Here's the lowest energy state for the neutrons. And as I start assembling a complex nucleus, I put the nucleons in one at a time. And let's just start with the neutrons over here. So I put one neutron in the lowest energy state, and let's say I put it in with its spin up. I can accommodate another neutron in that same state as long as I put it in with its spin down. And I work my way up. Each state can accommodate two particles, one with spin up with one spin down. And I can't put more than two into that state because they would not be quantum mechanically distinguishable, and the Pauli exclusion principle says that's not allowed. Okay? So I'm forced, as I add neutrons, to put them in ever higher energy states, just because of the exclusion principle. And again, That's very different than if the neutrons or protons had had integer spin. They would have then been bosons, and I could pile as many as I wanted to the lowest energy state. Now I do the same thing for the protons, except I start at a higher energy initially, and again I put the protons in, one with spin up, one with spin down, until I've accommodated all the protons and neutrons I need to make this particular nucleus. So what nucleus is that we're talking about there? How many protons have I got? Neon, okay, and what isotope? There are 12 neutrons, but it's neon, so what's the isotope? 22, neon 22, that's right. So that's how I would describe neon 22, and if you go back to the chart of the nuclides or look in the back of Lily's book, you'll find that neon 22 is stable, okay? Even though it has a couple more neutrons than protons, it is the lowest energy state for mass 22, and therefore it's the stable isotope of mass 22. Now you might think, okay, what's the big deal? But remember, way back on day 1 or 2, we were talking about the properties of the individual nucleons, and we noticed that the neutron is in fact radioactive. A free neutron beta decays with a half-life of about 10 minutes. And yet I stick 12 neutrons in this nucleus, and I just told you that this nucleus is stable. How come the neutrons don't beta decay? What is it about that diagram that would clue you into the fact that the neutrons can't beta decay? Right, that's right. Even though I've piled up 12 neutrons here, the highest energy neutron is still at a lower energy state than the first available proton. Now, if you think about it, if I want to do a beta decay, I take a neutron and I turn it into a proton. So if I wanted to take one of these highest energy neutrons and turn it into a proton, all the lower energy states that protons can be in are already filled. So the first available state the proton could go into is up there, but that's at a higher energy than that neutron, and therefore that's energetically forbidden. So this is a question that a lot of nuclear physicists don't know, but now you know the answer. It's the Pauli exclusion principle that's preventing the neutrons in most nuclei from undergoing beta decay, because the available proton states into which it could decay have already been filled. Okay? Now, of course, if I keep piling the neutrons on, eventually I get to the point where the neutron energy is above the first available proton energy, and then I will get beta decay. Okay? And so if you look at the very neutron-rich nuclei, that's the situation going on. I will get beta decay in that case. And similarly, if I piled up the protons, I could eventually get positron decay or electron capture if I get to a point where there's a lower energy neutron state available into which the proton could decay. Okay, but this is a very important consequence of the Pauli exclusion principle. Okay. Yes?
So a free neutron decays into a proton.
Right.
So does that energy...
Yes. Yes, it does. What you're pointing out is the fact that a free neutron is heavier than a free proton, and even heavier than a proton plus an electron, which is the neutral hydrogen atom. That mass difference does play into here. And so I've been a little cavalier in the way I drew this, but in fact you should take into account the intrinsic mass differences between the neutron and proton as well as the Coulomb energy difference in assembling that kind of diagram. But you're absolutely right. That is an important effect. Yeah?
It looks like with this diagram, you could have a nucleus of, say, 4 neutrons, and that would still be at a lower energy than...
So again, don't take it too literally, okay? Yeah, that isn't true. It's an interesting question, though, about whether you can assemble nuclei out of just neutrons. You might think you could, because after all, there's no Coulomb repulsion. They do attract each other via the strong nuclear force. Why not? So it turns out, when we were talking about the deuteron, I think I pointed out that there was only one bound state of the 2-nucleon system, namely the neutron and proton bound with their spins up. But you could try assembling 2 neutrons, and what you find is they fall apart right away. They don't stick together. You might ask about 3 or 4 or 10 or a whole lot, and people have done extensive experiments looking for these bound states of neutrons, and no one's ever seen one. So that's another consequence of the nuclear force, that it doesn't really like to have just arbitrary numbers of neutrons bound together. Other questions about that? In fact, an interesting sort of example of what you're talking about has to do with neutron stars. So you've probably heard about neutron stars, and we'll get to talk about them later when we discuss how stars evolve. And so a neutron star is an object that's about 10 miles in diameter, and it has the mass of our sun, roughly. Okay, so it's a very compact object, incredibly dense, and by the name you might assume that it's just a ball of neutrons held together by the strong force. It turns out it's not true. First of all, what holds it together is gravity, not the strong force. And secondly, it's not just neutrons. And the reason is because of this kind of thing, that if you just had neutrons, they would beta decay. So there have to be a few protons and a few electrons around to prevent all those neutrons from beta decaying. So again, it's sort of a macroscopic demonstration of the Pauli exclusion principle. And what people think is going on in a neutron star is the bulk of the star is in fact just neutrons, and there's a little thin crust, maybe a centimeter thick, where there are protons and electrons that are basically blocking all those neutrons from undergoing beta decay. But we'll talk more about that later. Okay, so I showed you this diagram on Friday, and the idea here was that in looking at this scattering experiment and seeing that if I have a nucleon approaching a target on this side or the other side, it turns out the deflection is in the same direction, but that means that one of them is an attractive interaction and one of them is a repulsive one. That implies that there is this component to the nuclear force that goes as this quantity L dot S, where L is the orbital angular momentum of the incident nucleon with respect to the target, and S is the intrinsic spin of the nucleon and the target. Okay, so given that, this woman, Maria Goeppert-Meyer, and some of her colleagues decided to implement this additional term in the potential. So they took the Wood-Saxon potential that we talked about the other day and added a spin-orbit potential. So they wrote it down as something proportional to L dot S, and the constant out front was something that they had to determine experimentally. This turned out to be extremely important and led to the modern version of the shell model. And for this work, she and her colleagues got the Nobel Prize in Physics in 1963. So this was a really big deal. So let's go back through this quantum mechanical addition of angular momentum and see how this plays out. So now I'm talking about a nucleon in a nucleus having both its intrinsic spin S and orbital angular momentum L. Okay? And these are vector quantities. So what we'll end up talking about to characterize a particular shell model state is the total angular momentum of that state, J. And J then is the vector sum of L and S. Okay? So let's just go through some arithmetic here. We can calculate the quantity J squared, and that is the square of the vector sum of L and S. And I just have to remember that these guys are vectors. So if I want to square this quantity, and when I do that, I get L squared plus S squared plus twice the dot product between those two vectors, L and S. And I can solve for L dot S. And the reason I'm trying to do this is to get that term in terms of something I can actually measure. Okay, because I don't really measure L dot S. But I measure J, and I can determine L, and I can determine S individually. So the dot product between L and S, then, just doing a little arithmetic here, is a half J squared minus L squared minus S squared. And remember that quantum mechanically, when I square angular momentum, I take the angular momentum and I multiply it times that angular momentum plus 1. So J squared is really J times J plus 1, L squared is really L times L plus 1, and S is really S times S plus 1. And these are all measured in units of h bar, so when I square them, it's h bar squared. Now, because we're talking about neutrons and protons, there's a very strong relationship between L and J. Namely, for a given value of L, J is either L plus a half or L minus a half. And so I can then calculate this quantity for J equals L plus a half or J equals minus a half. And I find that there are two different values. You can just plug that in here. So plug in J equals L plus a half and grind through. Plug in J equals L minus a half, grind through. And what you find is there's a difference between those quantities. In other words, L dot S when J equals L plus a half is not the same as L dot S when J equals L minus a half. And that difference, just from the arithmetic, turns out to be a half times 2L plus 1 h bar squared. And what that means is that there is a splitting in the energy between states according to whether J equals L plus a half or J equals L minus a half. So I take a given shell model potential in the version of the potential where I have just the Wood-Saxon potential. That would be one level. And now I add this L dot S coupling. That splits that one level into two. One goes up in energy, one goes down in energy. And the difference between them grows with increasing L. So the splitting gets bigger and bigger the bigger the value of L is.
So that value at the bottom is the change, is the...
Correct, correct. So they start with the same L, and they have the same S, but the vector sum is different between them, and this is the splitting between the two final states, right? So the splitting grows with increasing L, and it turns out in order to make this model agree experimentally with the observed magic numbers, it implies this spin orbit potential has to be negative. Okay, we don't know that a priori. We just know that there's some constant out front. We look at the observed magic numbers and figure out that to make them come out right, the spin orbit potential has to be attractive. And what that means is the state with J equals L plus a half will end up at a lower energy than the state with J equals L minus a half. You know, classically we tend to think that higher angular momentum means higher energy, but in fact in the nuclear case it's not true. So J equals L plus a half will be at a lower energy because that potential turns out to be attractive. So you've seen this kind of picture before. So this is a modified Wood-Saxon potential. The solid line was the curve we saw last week where we hadn't yet got to the idea of spin orbit potential. So this is the attractive nuclear potential then going to zero as the separation gets large. And here we're neglecting the Coulomb interaction between the protons. Now I add in the spin orbit, and what happens is the state with the spin, the intrinsic spin, parallel to the orbital angular momentum, turns out to have a lower energy than the one where the spin and the intrinsic angular momentum are not in the same direction. Okay? So I end up with two different potentials, if you like, because the spin orbit term leads to attraction if the spin and orbital angular momentum are in the same direction, and leads to a repulsion if they're in the opposite direction. Okay? And the net effect then is what we end up with over here. So we've worked our way through different approximations to the nuclear potential. The first was the infinite square well. Then we said, no, it's actually a finite system. We have a Wood-Saxon potential. And finally, when we take the Wood-Saxon and add the spin orbit term, this is the level scheme we predict. And you can see the splitting I was talking about. So for the first state, the lowest energy state, the 1s state, L equals 0. So there is no LS coupling because 0 times anything is still 0. But I go to the first state with non-zero orbital angular momentum, the 1p state. Okay, that means the principal quantum number is 1. That's what that 1 out front stands for. The orbital angular momentum is also 1. That's what the p means. Okay, that means L equals 1. And in the Wood-Saxon potential, there was one state with those quantum numbers. But if I have L equals 1, now I can have two different values of J, because I can have L equals 1 plus a half or J equals L minus a half. And according to what we just went through, the state with J equals L plus a half will be the lower energy state. And 1 plus a half in magnitude is 3 halves. So I end up with a 1p 3 halves state. That means principal quantum number 1, orbital angular momentum 1, J equals 3 halves is the lower energy state. And the one with the orbital angular momentum and the spin in opposite directions, so that's 1 minus a half, that's this state, 1p 1 half. Okay? And these numbers over here in parentheses indicate how many particles I can put into each of those states. So remember, I have to have each fermion in a quantum mechanically distinct state. That's what the Pauli principle says. So in the 1s a half state, the orbital angular momentum is 0. The total J is a half. I can put two particles into that state, one with intrinsic spin up, one with intrinsic spin down, and that's it. Now remember, I can put two protons into the state, and I can put two neutrons in. Okay? So that 2 refers to the type of an individual nucleon, either a proton or a neutron. When I go up here, what this is saying is I can put 4 particles into that state. And you say, wait a minute, I thought he said you could only put 2 in. Well, remember, you can have as many particles as you have quantum mechanically distinct states here. And so if I have a total angular momentum J of 3 halves, how many magnetic substates or how many Z projections of J do I have available to me? 2? What would they be? What do I mean by that? So remember, this angular momentum J, just like L and S, is a vector. So J is a vector that points off in some direction. And I'm saying the magnitude of that in this particular case is 3/2. And now I'm saying, suppose I have some coordinate system where I call that the z-axis. How many possible z components of that angular momentum vector do I have? Classically, they're an infinite number because this thing can be oriented in any old direction. But quantum mechanics says that's not true. Or, how come? What are they? What are they?
3/2, 1/2, -1/2.
Exactly, exactly. So I can have plus 3/2, I can have plus 1/2, I can have minus 1/2, and I can have minus 3/2. For any, and you can think of it as being different orientations of this vector with respect to my z-axis. And you know I'm a terrible artist, but something like that. So not only is the total angular momentum quantized, you can think of the projections of that angular momentum onto any axis you like as also being quantized. And in general, if I have a state with a spin of J, then I have 2J plus 1 Z components. And each one of those states is quantum mechanically distinct. And therefore, in this state, I can put 4 neutrons or 4 protons. Okay? When I go up to the next one, the total J is 1/2. 2J plus 1 is 2. I only get to put 2 particles in there. And now notice what happens. So these are the splittings between the major shells. So after I've put 2 particles in, I have to jump fairly high in energy to start putting in the 3rd, 4th, 5th particle. So 2 ends up being one of my magic numbers. 8 also ends up being a magic number because I can put 4 particles here, 2 here, that's 6, plus the 2 I already had. So after I put in 8 particles, again, there's a gap until I get to the next magic number, and so on. And remember before, when we were doing the infinite square well or the Wood-Saxon potential, we did okay in terms of matching up magic numbers with the observed ones up through 20. But then when we got higher up, we started missing because after 20, experimentally, the next magic number turns out to be 28, and that wasn't predicted in either of these approximations. But now, lo and behold, it is. Okay, because after I've got to 20, the next available orbital turns out to be the 1f7/2. So principal quantum number 1, orbital angular momentum L equals 3, total angular momentum 7/2, L plus 1/2. And I can put 2 times 7/2, which is 7 plus 1 particles into that, or a total of 8. And 8 plus 20 makes 28. So I predict properly the next magic number being 28, and I get all the rest of them right too. Okay, so I get 50, 82, 126. So this was what was needed to reconcile this so-called single particle model of nuclei with the observed shell structure that was observed. Okay? So if this doesn't make sense right now, please go over it because we're going to use this over and over again the rest of the semester. This is really, really important. Okay, and this is stuff you've seen before, but I want to go over it because it is so important. So remember, in this kind of model, we're talking about initially the angular momentum associated with a single proton or neutron, and we'll go through some examples in a minute. And that total angular momentum is the vector sum of the orbital and the intrinsic spin of that individual nucleon. And, right. So there's Z components of that angular momentum, and there are 2J plus 1 total Z components. So this you've seen before. And the other quantum number we're going to associate with these states is, again, something we talked about, namely the parity of the state. And that has to do with whether the quantum mechanical wave function changes sign under the operation of going from a coordinate system I call R to an inverted coordinate system minus R. Okay? And remember, if you basically stand on your head, the universe shouldn't change the way it appears to you. And so the square of the wave function, which is the only thing that matters really, it's the only thing you can measure, can't possibly change. So there are two possibilities for the wave function itself. Either it doesn't change at all, we call that positive parity, or it changes its sign, which is really not experimentally measurable, but it turns out quantum mechanically important. So if it changes sign, we say it has negative parity, and in either case, the square of the wave function remains unchanged. So it turns out you can associate a parity with the orbital angular momentum of the quantum mechanical state. So the parity turns out to be positive if L is even, 0, 2, 4, 6, etc. And the parity is minus if the parity is odd, 1, 3, 5, 7, 9. So remember this, the parity goes as minus 1 to the L. And that again will let us distinguish these shell model states, because not only do they have different orbital angular momentum and total angular momentum, they will have different parities. And that's not to be important when we try to understand why certain radioactive decays happen and others don't. It has to do with this parity as well as angular momentum. Okay. Now, experimentally, I think I also said this before, if you look at complex nuclei and look at those nuclei that have both even numbers of protons and even numbers of neutrons, these are called even-even nuclei. All of them have ground states where the spin is 0 and the parity is positive. This is an experimental observation. And that's, again, a reflection of the fact that when we're putting these neutrons and protons in to complex nuclei, they like to pair up because of that spin-spin part of the nucleon-nucleon interaction. So if I have an even number of protons in my nucleus, each one of the protons will find a partner to pair up in such a way that their intrinsic spins and orbital angular momentum add up in such a way to give you a total spin of 0. Okay? And similarly for the neutrons. So experimentally, even nuclei all have 0 plus ground states. We're going to talk about more complicated nuclei in a minute where we don't have even situations. And we might even talk about odd nuclei, which are the most complicated. And the thing to remember is that if you're talking about a complicated nucleus and you want to know the parity of that nucleus, you have to know the parity of each individual nucleon, that is either plus or minus, and the total parity, which we call pi, is the product of all the individual parities. Okay? So in an even nucleus, they're all going to be positive or negative. They're all going to multiply out to give you a positive number. Okay? In an odd A nucleus or an odd one, that may or may not be the case. Okay. So let's talk about the simplest possible nuclei, the closed shell ones. And what I mean by that is a nucleus that has a magic number of both neutrons and protons. Okay, so the simplest one is the alpha particle, helium-4. It's got 2 protons and 2 neutrons. The next one is O16, 8 and 8. Okay, 8's the next magic number. If I have 8 protons, I'm oxygen, and 8 neutrons is O16. The next one, calcium-40, 20 and 20. Okay, and similarly, I can go up the chain. This isn't all of them, but the last one that we know about so far is lead-208, 82, 126. And I don't want to stress this too much, but the analogy is like the noble gases in atomic physics. Okay, so what we're saying is we've closed the nuclear shell with neutrons and protons. These guys are, in a nuclear sense, more inert than their neighbors. And we'll see exactly what that means in a little bit. And so in atomic physics, you're used to thinking of helium, neon, argon, etc., being noble gases. They don't react very much chemically. Well, these guys don't react as much in the nuclear sense as their neighbors. In the atomic case, it's closed shells of electrons. In the nuclear case, it's closed shells of neutrons and protons. Okay, the next simplest situation is what we call a single particle nucleus. Okay, and what that means is I take a closed shell nucleus, like in this case that we're illustrating here, helium-4, and then I add either a neutron or a proton. Okay, so I'm back to a drawing like Lily's where I'm not accounting for the difference in the Coulomb energy. For these purposes, it doesn't matter because all I'm trying to do at this point is to figure out what do I expect the ground state spin and parity of that nucleus to be. So let's first look at helium-5. So helium-5, I know that since it's helium, that means I've got 2 protons. And the fact that it's mass 5 says I have to have 3 neutrons. So where can I put those 5 nucleons? Well, the 2 protons go just fine in the lowest energy state available, the 1s², because one of them will have his spin up and one will have his spin down, and they're different from one another. When I do the neutrons, I can put 2 neutrons in that 1s a half state, but I can't put the third neutron there because that would not be quantum mechanically distinct from his brothers or sisters here. So I have to put him in the next state available, which is the 1p3 halves. The shell model says that's the next available state, and so I have one nucleon, one neutron, in the 1p3 halves state there. And similarly, if I go to lithium-5, it's the same situation, except now I've got 3 protons and 2 neutrons, and so that one extra proton, the third proton, would have to go in the 1p3 halves orbital in lithium-5. And so I would predict on the basis of this that both of these nuclei should have a spin and parity of 3 halves minus in their ground state. 3 halves because that's the J value of that 1p3 halves orbital, and parity being negative means there's an odd orbital angular momentum. P means L equals 1. You have a question? Just checking. Okay, good, okay. It turns out neither of these nuclei are stable, but that doesn't matter for this argument. So these are nuclei that have one nucleon, that is one proton or neutron, outside a closed shell. And these are analogous in the chemical sense to the alkali metals, okay? In the sense they've got one extra electron hanging out, lithium, sodium, potassium. They like to lose that electron to become a closed shell atom. They're very reactive in that sense. And these guys similarly would like to lose that one extra neutron or proton to get back to being a closed shell nucleus, okay? So nuclei one particle away from closed shells are very either unstable under certain circumstances, or they will react in a nuclear sense and transform themselves back to a closed shell. The other simple situation is what's called a single hole nucleus, okay? And what this means is that they are one neutron or proton away from being a closed shell, meaning they lack one neutron or proton from being a closed shell. So we talked about O16 as being doubly magic. Let's look at O15. Okay, so it's got a magic number, 8 protons. And if we go through the shell model scheme I showed you a minute ago, we get to put 2 protons in the 1s a half, 4 protons in the 1p3 halves, and 2 in the 1p a half. So I get 2 plus 4 is 6 plus 2 is 8. Okay, I close the proton shell. And if I have 7 neutrons, I fill it up to here, and I have one vacancy, one hole, as it's called, in the 1p a half orbital. Okay? And so I would predict on the basis of this that this nucleus would have a spin and parity in its ground state of 1/2 minus. Okay? Half because that's J, and since it's a p orbital, the orbital angular momentum is 1, it'd be negative parity. And similarly for nitrogen 15, same story, except now I've got the closed shell of neutrons, one vacancy in the 1p a half orbital for the protons. Again, I predict spin and parity of a half minus. Turns out that's correct if you go look in the back of the book. Those are the correct spin and parities for these nuclei in their ground states. And this is why, because this is the way we fill up the shell model orbitals. And these are analogous to the halogens, okay? Very similar in structure to things in the chemical sense, like fluorine, chlorine, bromine. These guys are very, very reactive. They're one electron away from being a closed shell. And the way they close their electron shells is to grab an electron from somebody else and become a negative ion. So F minus has the same configuration electronically as neon, that is a closed shell. And similarly for chlorine and bromine. These guys would like to grab a neutron or proton from somebody else to close their neutron or proton shells. Okay? Okay. So this is a similar diagram to what I just showed you. Here's O15 with one neutron away from being a closed shell, lacking one neutron. Here's O17. It's got one neutron beyond the closed shell. So here I've got doubly magic neutrons and protons. I add the next neutron. It has to go up into the 1d5 halves orbital. So these are the kind of things you want to start getting familiar with. Yes?
So that one would be a 5 halves minus, and that would be a 1/2 minus? Or?
Okay, so you want to know the total spin and parity of the nucleus. Okay, so let's look at this. For O15, what's it going to be? The rule is we take the last nucleon, the unpaired neutron or proton, and we take its J, that will be the ground state spin and parity of that nucleus, and the ground state spin rather, parity will be determined by the L value of that last unpaired nucleon. So in the O15 case, what's the J of that last unpaired neutron? 1/2. So J is going to be a half, And will the parity be positive or negative? What is the orbital angular momentum associated with that state? 1. That's what the P stands for. And the rule of thumb is the parity goes as -1 to the L. So what parity would I assign? Negative. So this we would say is a half minus ground state spin and parity. Okay, for this one, what's the argument you would go through there? What's the J going to be? 5 halves, because the last neutron goes into the 1d 5 halves. And what will be the parity? Positive, because L equals 2. That's what the D means. So L equals 2 minus 1 to the 2 is plus. So we'd predict on that basis the ground state spin and parity of 017 should be 5 halves plus. And that turns out to be true. Questions about that? It's really important. Because now you start getting nuclei like this, okay? This is out of Lilly. And these are energy level diagrams for a whole bunch of different nuclei. And these, again, are ones that are near doubly magic cases. So the top row are all nuclei near the doubly magic 016. Okay? So here we've got N15, which we talked about a minute ago. It's 1 proton away from being a closed shell. 015, we also talked about 1 neutron away from being a closed shell. And you can see we get the correct configurations. They both have ground state spin and parities of a half minus because of the shell model configurations where those odd nucleons go. Now, nuclei are complicated objects, and all I've been talking about so far are their ground states, the lowest energy state. So if you go over here and look at 017, we just discussed the ground state spin and parity of 017, and we said in the shell model it should be that that last neutron goes into a 1d 5 halves orbital, and therefore the spin and parity should be 5 halves plus, and lo and behold, experimentally it is. But what these other lines represent are excited states of that nucleus, meaning different configurations of the neutrons and protons. And in fact, there's an excited state which is at 0.87 MeV. That's what the units are here. It's 0.87 MeV above the ground state, and it turns out it has spin and parity of a half plus. And you have a homework problem this week trying to understand the assignments of these excited states. Why is it that the excited states have the ordering that they do? And if you go back to the shell model diagram, you'll see that they pretty much follow the expectation if you just take that odd neutron in this case and put it into successively the next available quantum mechanical state according to the shell model. We'll see later on that isn't always the case. When you get into more complicated nuclei, sometimes you can predict the ground state spin and parities correctly, but in some cases you don't. And in other cases, you would then say, okay, I get the ground state right, but what about the excited states? They don't follow the order you would expect. And in a minute, we'll see why there are shortcomings to what we're doing, because we've made a lot of approximations in coming up with that shell model scheme that we've been talking about. So again, these kind of diagrams are things you want to get very, very familiar with, because you're going to see them over and over again through everything else we do. And the idea is there's always a lowest energy state for each nucleus. For whatever number of neutrons and protons, it's just the one that turns out to be the lowest energy. But there are a very large, almost infinite number of excited states in most nuclei, because these are quantum mechanical systems. You have many, many particles in something like lead-209, and you can imagine there's almost an infinite number of ways of arranging them. Okay, so let's look at some shortcomings. I alluded to the idea that we've made some approximations in getting as far as we have, and so let's look at some slightly more complicated nuclei. And so remember, calcium-40 was doubly magic. I had 20 protons and 20 neutrons. So let me just go 1 neutron beyond that. So calcium-41. Let's go back to the shell model for a minute. Okay, so calcium, doubly magic, 20 protons, 20 neutrons. I want to make calcium-41 now, so I'm going to put 1 neutron more in. And the first available state, according to the shell model, is this 1f7 halves orbital. So I would predict then that the ground state spin and parity of calcium-41 should be 7 halves and negative parity because F means L equals 3. Okay, fine. So I go and look at calcium-41, And lo and behold, the ground state spin in parity is 7 halves minus. Okay, good. I go and look at scandium-41. Scandium-41 and calcium-41 are what we call mirror nuclei. Remember, we talked about those a week or two ago, meaning I just interchanged the protons and neutrons. So in calcium-41, I've got 20 protons and 21 neutrons. In scandium-41, I've got 21 protons and 20 neutrons. Okay? Shouldn't make any difference in terms of the shell model, because that extra proton should go in the 1f7 halves orbital. And lo and behold, the ground state of scandium-41 also has a spin in parity of 7 halves minus. But look what happens when I start going to the excited states. So in the excited states, I would imagine taking that last unpaired nucleon, in this case a neutron, in this case a proton, and just put them in the next available shell model state. So if you go back, you would predict the next one should be a 3 halves minus, and lo and behold it is, in both cases, although the energies are slightly different. But then when I start getting up higher, the ordering starts being different. Okay? That is, the ordering here, 3 halves minus, 5 halves minus, 5 halves plus, is not what I see over here. And according to what we've said so far, they ought to be identical. Okay? And they're not. Similarly, if I go over here to a slightly more complicated nucleus, here's calcium-43. So I've got 3 neutrons beyond the doubly magic situation. Okay, so I put 3 particles into the 1f7 half state. And if I go back a minute, okay, so I'm going to put 3 neutrons into the 1f7 half state. And now if you think about it a minute, I've got 3 neutrons now, each of which has j equals 7 halves. Okay, that seems complicated, okay, to try to figure out what is the total j going to be of that state. But remember, the neutrons and protons like to pair up. So when I start assembling this nucleus, this calcium-43, what's going to happen is I put in the first neutron beyond calcium-40. It'll have its spin in a certain direction. The next one will pair up with it so that the total spin provided by those 2 neutrons adds up to 0. Because remember, we just went through the discussion that experimentally all even nuclei have ground state spin in parity 0 plus. So calcium-42, which would be the nucleus I get by adding 2 neutrons to calcium-40, has a ground state spin in parity of 0 plus. So those 2 neutrons just go in and pair up and give me total angular momentum 0. So when I add the third one, it has no partner to pair up with. Its spin will contribute a total of 7 halves to the nuclear spin and negative parity. So I predict the ground state spin in parity of calcium-43 to be 7 halves minus also. And lo and behold, that's what I see. And similarly, if I go to another mass 43 system, scandium-43, again I see 7 halves minus, titanium-43, again 7 halves minus. But as soon as I get to the excited states, now the ordering gets screwed up. Okay? And again, according to the shell model, these ought to all be identical. Okay? And they're not, because the shell model isn't perfect. So when you have a homework problem or you have an exam question and someone says, use the shell model to predict the ground state spin in parity of something, or predict the excited states of a given nucleus, it's a good guess, but it's not necessarily going to give you the right answer. Okay? And when we get to even nuclei and odd nuclei later on, we'll see other models that are necessary to explain the excited states there. But if you're told to use the shell model, use it. Use the simplest thing you can think of, and that's as good as you can do within that model. And here are some more shortcomings to show that not only do you sometimes not get the excited states right, you don't even get the ground states right. So here I am not very far away from doubly magic 016. So I'm only at fluorine 19 and neon 19. Okay? So I'm 1 proton away and 2 neutrons away from doubly magic. Okay? So let's look at fluorine 19. I've got 9 protons. That's what makes it fluorine. So I start filling up my orbitals, and the last proton, according to the simple shell model, should go in the 1d 5 halves orbital. Okay? And that would predict that the ground state spin in parity should be 5 halves plus, because L equals 2 here. Well, experimentally, it's a half plus. Okay? Similarly for neon 19, I do the same argument, except now it's the odd neutron, which again should go into the 1d 5 halves. Again, I expect it to be a 5 halves plus. Experimentally, it's a half plus. Okay? So for some reason, this odd proton or odd neutron would prefer to be up here than here. Okay? So not only do you sometimes get the excited states wrong, sometimes you even get the ground states wrong. And part of the reason is that you may remember we were assuming all along that nuclei were spherical. And it turns out it's not true. A lot of nuclei are deformed, and then the approximations we made are no longer valid. And the further I get away from closed shells, the more deformed nuclei tend to be. The closed shell nuclei, remember, we showed you the evidence the other day for the closures of the shells, and one of the observations that said there was something special going on around the magic numbers was the electric quadrupole moments of those nuclei were especially small. And remember, quadrupole is a way to measure how non-spherical an object is. So if the quadrupole moment is small, that means you're nearly spherical. And once we get away from that spherical shape, then the approximations for the shell model are no longer valid. It turns out there are ways to modify the shell model to include deformations, but that's beyond the scope of this class. Another property that you talked about, I think last week when I was away, was the magnetic moments of nuclei. The fact that the neutrons and protons in a nucleus are moving around. A proton moving around in a circular orbit or something like that, you can think of as a current loop. And classically, a current loop produces a magnetic field. And so we can associate a magnetic moment with that orbital motion of a proton in a nucleus. And furthermore, the neutrons and protons themselves have intrinsic magnetic moments due to the fact that the quarks are running around inside the neutrons and protons, and they each carry electric charge. So if I start taking many protons and neutrons and assembling them to make a complicated nucleus, that nucleus will end up having a magnetic moment. And it has a magnetic moment for two reasons. One is the intrinsic magnetic moments of the individual neutrons and protons, okay? And then there's the orbital part contributed by the fact that they're moving inside the nucleus. Now, it simplifies a little bit because the neutron is electrically neutral, and so whether it's moving or not doesn't matter. That doesn't generate an electric current. And so that motion does not contribute to the magnetic moment. So there was a formula written down last week for the magnetic moment of a nucleus. It's measured in nuclear magnetons, and there are two contributors to it. One is the orbital part, and there's a weighting factor, G sub L, which is unique for the neutron and proton. For the proton, it's 1. For the neutron, it's 0 because the neutron has no electric charge. And then there's another factor which contributes, which has to do with the intrinsic magnetic moments of each neutron and proton, and these are the values appropriate for neutrons and protons. They differ in magnitude and they differ in sign because of the different quark configurations of the neutron and proton. You can then take this information and the shell model and predict what the magnetic moments of individual nuclei should be. And the predictions are different for J equals L plus a half and J equals L minus a half. And you can understand that qualitatively because it just has to do with the orientation of the orbital motion with respect to the intrinsic spin. Okay? And so depending on whether J equals L plus a half or J equals L minus a half, you get a different magnetic moment. And you can then calculate what that should be for a whole bunch of different nuclei. And what's being plotted here is the magnetic moment as a function of the J of the value, the J of the odd nucleon. In this case, it's protons. In that case, it's neutrons. And these solid lines are what you would predict from that formula I just wrote down. Okay? If J equals L minus a half, you would predict this value for the magnetic moment. If J equals L plus a half, you would predict the upper one. And what you see in the dots are the experimental values. In general, they lie in between these two. Okay? So the predictions overestimate both for J equals L plus a half and J equals L minus a half what the magnetic moment should be. But in general, the trends are correct. Okay, that is, as the total angular momentum goes up, so do the magnetic moments. Okay, and initially you would think for a neutron the magnetic moment should be 0, but in fact it's not. In general, the magnetic moments are smaller for neutrons, but not 0. And similarly for the electric quadrupole moments, again, the measure of the non-sphericity of a nuclear system. You can calculate this quadrupole moment. You can calculate it quantum mechanically if you know what the wave function is. If you go back and look at the definition of a quadrupole moment, it's this funny quantity. It's 3z squared minus r squared. So remember, we're looking at an individual neutron or proton running around in a nucleus. It has a position that we can quantify by x, y, and z coordinates. R is the square root of the sum of x squared plus y squared plus z squared. And if the particle is moving around in a spherical orbit, then on average, z will be 1/3 of r in magnitude, and this thing will integrate to 0. If it's not moving in a spherical orbit, then there will be a difference between 3z squared and r squared, and I'll end up with a quadrupole moment. So if you consider an odd A nucleus, so I've got, let's say, one proton outside a closed shell, and let's assume, for the sake of argument, I've got the z component of j being equal to plus j. So it's aligned as nearly as possible it can be to the total angular momentum. If I think about that a minute, I've defined my z-axis in such a way that j is nearly pointing along it. For that to happen, the particle has to be moving mainly in the xy plane so that j points up out of that plane, namely in the z direction. That means it's spending most of its time in the x and y direction, not in the z direction. So that means that r squared is going to be bigger than 3z squared, and that quantity will end up being negative. So we would predict approximately that this quadrupole moment should be something like minus r squared. And the real point of this is that we predict a negative quadrupole moment for a particle like that. If I've got an odd neutron, the charge of the neutron is 0, I expect a quadrupole moment to be 0. Okay? What do we see experimentally? I go through shell model states given over on the left here. What I would calculate the quadrupole moment of the nucleus should be if I had one odd either proton or neutron in that orbital. These are the calculated values, and these are what I see experimentally. For odd protons, they are mainly negative. That's the important thing. Quantitatively, they don't necessarily agree so well with the calculations, but they are negative. And remember, I predicted the quadrupole moment for an odd neutron ought to be 0. They're not exactly 0, but in general, they're smaller than the ones you get for the odd proton. And so qualitatively, it's giving us the right kind of prediction. Okay, that's a lot of stuff on the shell model. It's really important. I can't say it enough. So go through the homework. If you have questions, come and see me. Come and see the GSIs. We'll pick up here on Wednesday, and we'll move away from the shell model and start talking about more complicated models we need to explain even nuclei and their excited states. Okay, see you Wednesday.